All right, guys, I think I might go ahead and get started. Just want to thank you guys for coming in on a weekend, and hopefully the air conditioning will keep working. It's been pretty hot for the last couple of days, but I think it's supposed to be cold and cloudy tomorrow, so it's going to change dramatically again very shortly. But I'm going to go ahead and get started. I hope everybody out there in Zoom can also see me. I've put up the uh, Canvas homepage here really quick, just to, I don't want to do a lot of like logistics here, but I just want to point out in the final exam resources folder, there is this thing about this review session here. So I'm going to be going through a lot of these problems. Maybe not all of them today, because I'm also going to do another review tomorrow. And maybe between the two sessions, I'll go over most of those. But I also have a bunch of other problems too. Probably way more than I really have time to do even in 2 days. If we go to the pages section, I didn't get a chance to show you guys this during class last week. There is a review session video here, but actually what it is, it's a little different than the other midterm videos that I showed you. What I actually have is what I'm calling video A, video B, video C, video D, and there's like 8 or 9 of them. You don't need to watch all of these, but what I have here is I tell you how many minutes the video is. The first one's 106 minutes, but most of them are more like 30 minutes, 24 minutes, 13 minutes. And I kind of talk about like what's in each video. It's not as organized as I would like, but it's at least something. So for example, if you realize that you just want a general overview of chapters 1 through 5, right? There is a 30-minute video. There's no problems in that video, but it's just an overview. So, because I'm going to mostly be doing problems today. So if you feel like, yeah, the first half of the semester is a little fuzzy for me right now because it's been a while, you could just turn this on for a half hour and just kind of watch it through. And then you can just see, I tried to put what the topics are. Again, it's not as organized as it could be. Someday in my next life, I'll try to organize these a little bit. But you know, here's a section, a 13-minute segment on theoretical problems about eigenvalues. I know it's a little hard to read, but anyway, so I just wanted you to know that this is here too. I didn't show this last week in class, but if you're looking for, if you'd rather learn by listening rather than just trying to read a whole bunch of stuff, you could watch some of that. And maybe after you see some of the problems I'm going to do now, that might trigger your own feelings about what you need to review, right? That's kind of a part of the purpose of the review session, is just to kind of get things back in your head again. It's not necessarily you're going to walk out of here ready to take the test, but at least you're going to know what your strengths are, what your weaknesses are, where you want to spend your time. I know we only have well, for some of you, we only have a couple of days. That's not a lot of time to do a huge amount of stuff. But at least we can do the best we can with the time we have. So I'm going to turn that off for now. And just ask, does anybody have any questions for me before I start just sharing out some problems? Yeah, Edgar?
You did mention we don't have to tell you what day we show up for the final.
That's right. That's right. So if you are studying along, like, I mean, some people don't have a choice because their schedule, but if you have a choice to do it either on Tuesday or Thursday, and you can be trying to go for Tuesday, and then if you decide not really ready, you could wait till Thursday to take it. Yeah. So you don't have to tell me in advance. Because I've reserved a second room. So if everybody shows up from both of my classes at the same time, then I'm just gonna take 2 rooms and give everybody the exam all at once. So we'll see how it goes. I'm pretty sure there's gonna be a pretty even balance. I don't think it's gonna change that much. Most people probably will take it at the same time they normally would take it, but I just wanted to give that option. Yeah. So anything else?
I'm gonna go section by section, like in order.
With this?
Yeah.
Not necessarily.
Okay.
No, I wanna go in order of what I think people need the most review on, and also what I think might be. I don't know exactly what everybody's weak points are, but what I think might be some weak points, or at least some rusty points. That's what I'm gonna do. So it will be a little bit mixed up, but on the other hand, that's kind of how you probably take the tests too. You kind of jump around a little bit. I think on the exam, I'll try to put the problems somewhat in order. from the beginning of the semester to the end, but I don't know how it's gonna work out. I'm still working on the test, so be a little bit of time, yeah. Well, actually, speaking of that, I'm gonna start with a problem that is kind of from the beginning of the semester. So I'm gonna just number these, and by the way, the numbering I'm using is not gonna be the same as the numbering in the materials. So I don't wanna try to keep track of that because I am gonna jump around a little bit. So I'm just gonna start with number one, and I just wanna do some problems that are hopefully gonna be high impact, heavy, well, try to give you as much review as possible as quickly as possible, right? So that's kind of the idea. So, because I know we don't have a lot of time. So I'm gonna try to solve this differential equation. And here it is. I'm gonna do y prime minus 3/2x times y equals 6y to the 1/3 times x squared ln of x. And it should probably be stated here that we can't take the logarithm of a negative number, so we'll just assume that x is greater than 0. Okay, now, you might remember from our last class this past week, I sort of gave you a little bit of a roadmap. If you have a differential equation, kind of some questions to ask yourself. One of the questions was, is this a single differential equation or is it a system of differential equations? Because that'll affect a little bit what we're gonna do. What are your thoughts on that? Is this a single differential equation or is it a system? It's a single, there's only one unknown function. That's actually the key. There's no vectors here. It's like normally if it's a system of differential equations, you'll have a vector equation that looks like this one. So that's chapter 9, which is what we learned recently. I probably won't spend quite so much time on this today, just because that is fresher material. This is definitely a single differential equation. What is the order of this differential equation? First order, right? I have one derivative only and nothing higher than that. So when we think about where did we learn how to solve first order differential equations, that takes us way back to the start, right? Even before we did any linear algebra, we learned how to solve first order differential equations. So we had several kinds of first order differential equations. I reviewed them briefly on Thursday. There was the separable ones, the linear ones, and then we learned about Bernoulli and homogeneous of degree 0 differential equations as well. Does anybody happen to remember, based on that, which type this is?
Separable.
Separable, pardon?
I just said.
Well, you said Bernoulli. Separable, Bernoulli, any other? Don't want to break the tie, Anthony? Homogeneous of degree 0. I may have a vote for another option. Okay. Does anybody- Linear. Okay, so let's remember, let me talk first about the homogeneous of degree 0. If you remember, for homogeneous differential equations of degree 0, what you need to do to identify them is actually solve for the y prime. So that would involve moving everything to the other side of the equation. And this right-hand side is some function involving x's and y's. And what I wanted to remind you about homogeneous differential equations of degree 0 is that if you were to, this is the test we used, if you attach a t to every single x and every single y on the right-hand side, for it to be homogeneous of degree 0, it is not supposed to change what you have. So like if I do that here, so I'm gonna put a question mark on this because I don't know at the moment. So I'm testing for homogeneous of degree 0. Right? So if I attach a t to every single x and every single y on this right-hand side, then what I'm gonna end up with is something that looks like this. So I literally want to put the t in with the x or y in the parentheses. Okay, so everywhere I had an x, I now wrote xt. Everywhere I have a y, I wrote yt. The question is asking you, for homogeneous of degree 0, will all of those t's cancel back out again and just return me to the original right-hand side? So I can see, for example, that these t's right here cancel. Right, which means that you really do, the first part of the right side is still the same, yeah? That has not changed. But what about the rest of it? Can I cancel the t's that I see over on the rest of the right-hand side? Not so much, right? Not so much. I mean, I don't have any denominators here. So I mean, I can factor the t's out. But I can't get them to completely disappear, right? I can't get them to cancel. So I would say that this is not equal to the original f of x, y. So I'm gonna say a no on this one. In this particular case. Now, for those of you who were voting for separable, the thing with that is you have to algebraically ask yourself, can you move things around to get all of the x's on one side and all of the y's on the other side? So like I can see that I have a lot of x's on the right side. I could divide this cubed root of y over to the left side. You know, so let me just write that down. This is just purely an algebra manipulation. Like I could try to do this so that I only have x's on the right side. But I have to have, whoops, something's wrong. This is supposed to be a minus, I'm sorry. So this is what I would have here. But so I have all these x's on the right side, but if I look at the left side, I still have x's and y's. And also remember that this y prime really has an x with it as well, because it can be thought of as dy over dx. So the question would be, is there any algebra that you know of under the sun that could possibly get these x's to the other side without having to drag any of the y's back over to the other side again? And that is also looking pretty impossible. Like if I tried to move this x to the other side, I could do that if I multiplied through by x, but then I'd create an x here, right? So there's an x on the bottom here, and there's no x over here on the top or the bottom, but if I move this x to the other side, I have to also put an x on top right here. The algebra is not going to allow us to do that. So in terms of, I mean, it's a perfectly reasonable thing to do. In fact, that's usually my first thought, is to see, can I get the variables separated? And if I fumble around with the algebra for more than 30 seconds and I'm not able to get it separated, I usually will punt on that and probably assume it's going to be something else. When things are separable, you usually have to be able to completely factor them, and you usually don't have like if this was y prime times 3 over 2x times y, then it would be easy to, like, you have no pluses or minuses to deal with. You can then take reciprocals of move things around much more easily. But this minus sign is really what kills us here. Okay. So that brings us to, if it's not homogeneous and it's not separable, that brings us to the Bernoulli option or linear option. So I'm just going to remind everybody here, you're going to want to know this. The form of a linear differential equation is y prime plus p of x times y equals q of x. This is for a first order linear differential equation. Okay, and some of you might be wondering, well, if it's linear, why can't I use the stuff from chapter 8 to solve a linear differential equation? Really, the reason is that in chapter 8, we were mostly focusing on differential equations that looked like this. So more recent, in other words, the more recent material that we did, our differential equations looked like this. I often called this, L of y equals f. And the thing about this is that the A0, the A1, the A2, those are all viewed as constants. When they are constants, then you have, the e to the rx solution, and you can solve for r using the auxiliary equation, all of that stuff from just a few weeks ago. But here, this is a more general form of a linear equation where the coefficients, the p and the q, are not necessarily constant numbers. They actually can be functions of x. So based on that, we have to go back to the earlier methods for this. And what we learned, of course, way back in January, is that this is solved by using integrating factors. Yeah, so there's this thing called an integrating factor. Let me just remind you about that while I'm at it here. So this is like a quick review of chapter 1. The integrating factor here, guys, would be, does anybody remember the formula for it?
Either the integral P y CPX dx.
Exactly, yeah, e to the integral of p of x dx. This goes way back to the start of the semester. And what happens is, the way it was derived, you don't need to remember the derivation, by the way. But what happens is that when you multiply through the entire differential equation by I, what you do is you end up creating a derivative of a product. And it's exactly the product of the integrating factor times the unknown function that you're trying to solve for. And on the other side of the equation, you've multiplied through by I, and so the q of x now picks up an I of x. So this is actually what happens when you apply the integrating factor. So I'm going over this, guys, because there's a few things to memorize here. You need to know this form of a linear differential equation. You need to know what the integrating factor is going to look like, the formula for that. And then, unless you want to derive it, which I don't recommend, you need to know this one as well, that the derivative of the product of I times y is q times I. Yeah. Once you get to here, you're in pretty good shape, because to solve for y now, you can kind of see what you need to do. You have to get rid of the derivative by integrating both sides. And then you have to divide through by I to get the y by itself. So that's how we do these. We're going to see this today because we're going to be reviewing this. But this is just a quick reminder about first order linear equations. Now, having said that, is this one first order linear? No, why not? What's the real reason? What's the real problem with this that makes it not linear?
Why?
The y on the right side to the 1/3 power, right? That's not part of what you see on the right side over here. It's supposed to be only in terms of x. So I see that y to a power on the right side, and that's a red flag that this is not going to be linear. However, if you remember, so we've now ruled everything out. The only thing left is the Bernoulli equations. Yeah, question?
Yeah, even if y is to the first power, it's still not linear. Right?
If y was to the first power, it's not in the form of the linear equation as stated here. It would be possible, if this was y to the first power, to factor the y. It's like you could actually move this term to the other side and then factor out the y, and you could make it into a linear equation with rearranging it. So I would actually argue that if this was y to the first power, I would probably move this over to the left side, creating a 0 on the right side. And then what you'd have here is a y prime with a very large p of x times y. So this would be a case where if this was y to the first power, you could manipulate it into a form of a linear equation. And in a minute, I'm going to show you another reason why, if y was raised to the first power, that you would want to do it that way. You'll see in a second. Okay. So anyway, we have a 1/3 power here right now on this thing. But if we look at the form of a Bernoulli equation, it's very similar to a linear equation. So I'm going to, right away, guys, I'm writing down a bunch of equations that are pretty far back in the semester that we're going to need to learn. So the Bernoulli equation is very similar to the linear one, except now on the right side, we have a y to a power of n. Okay, so you just need to keep these two straight. And now when you see that box, it's like, oh yeah, this is perfect setup for this equation, right? So we have a y prime, we have a p of x times y, we have a q of x on the right side with a y to a power. And that power, which is called n, would be 1/3 for this equation. Now, the thing is, for a Bernoulli equation, you have to do a change of variables to solve it. And I went over this, obviously, in a lot of detail when we first learned it. The change of variables equation, guys, is u equals y to the 1 minus n power. And now this gets to the other reason why you don't really want to allow n to be 1 here. So Edgar was asking, well, what if this was just y to the first power? If it was y to the first power, then your n would be 1. And then that would mean that your u, which is, yeah, right, y to the 1 minus 1, right? So you'd have a 0 exponent. Y to the 0, of course, is 1. That's not really changing variables anymore. That's just changing a u into a 1, which doesn't serve the purpose that you want. So this is actually what you want, okay, for the change of variables. So I would recommend that you don't do this for n equals to 1. Okay, so let's just put that idea to rest. The other equation that you need to know here in order to successfully solve these problems is you need to know how to convert this now into a linear differential equation. So it always, Bernoulli equations will always be transformed into linear ones. And what is the formula for it? Well, you'll have u prime plus 1 minus n times p of x times u equals 1 minus n times q of x. So I'll put a box around that as well. There's actually all three of those equations. You really need to know them to be able to solve Bernoulli differential equations. Yeah. Okay, and notice what's happened is really the original Bernoulli equation is not changed very much. The only thing is the y's turned into u's, and we tacked on a 1 minus n in front of both of the other terms. That's all that really happens there. So with that in mind, guys, I think that our problem up here that I'm asking us to look at is Bernoulli. It is a Bernoulli equation, so let's practice it. Let's go through the method here and solve this with the Bernoulli equation. So guys, right here, so now I'm ready to do the solution. If I write down the word Bernoulli and don't do anything else, I already probably got a couple points, right? If I go even further and I say what n is equal to, might even be a couple more points, right? So it's a lot of partial credit step by step. So don't just leave it blank. If you're like, I'm not sure how to do this, I'm gonna leave it blank. No. If you know it's Bernoulli, write that down. If you know what n is, write that down. I can give you, if you know the change of variables, u equals y to the 1 minus n, write that down. So in this case, 1 minus 1/3 would be 2/3. So our change of variables is u equals y to the 2/3. So you've already got a decent partial credit here without even having to break a sweat yet, right? So you can just kind of get that going right away. Okay, once you've done that, we tend to just leave this. You don't need to use it right away, but we will use it later. Once we've solved for u, we will need this equation in order to solve back for y again. Because remember, your final answer should be in terms of y, which is what's showing in your problem. So I am going to have to use this box here, but not until the end. So in the meantime, what I really need to do next is go to the linear form that I'm supposed to end up with and just write it down. So what I'm going to have is we get u prime plus 1 minus n is 2/3 of whatever the p of x was. And I want to remind everybody here, this minus sign is part of the p of x. So be sure to not lose track of that. We still have minus 3/2x times u. And then on the right-hand side of the equation, notice that on the right-hand side of the equation, we've lost the y to the n here. We're just going to keep everything else, the 6, the x squared, the ln of x, and the 2/3. Okay, so I have all of that. And now let's clean this up just a little bit. The 2/3 and the 3/2 cancels. We still have a minus 1/x times u. And then 6 times 2/3 is 4x squared ln of x. Okay, and this is supposed to now be linear. So this should be a linear differential equation. So to solve a linear differential equation, I now have to use the integrating factor, right? So the I of x is going to be e to the integral of p of x. But let me remind you that we are now talking about this p of x, not the p of x from the original problem. So the p of x from the original problem is now gone, and we're working with the p of x right here. So that's the negative 1 over x that we have to integrate in that exponent up there. And as you guys are well aware, the integral of 1 over x dx is the ln of, normally it's the absolute value of x, but I've been very careful that x is already positive, so I don't really need to worry about that. What is e to the negative ln of x going to reduce down to?
X to the negative 1.
X to the negative 1. So this negative sign gets thrown up as an exponent here. So just remember your laws of exponents a little bit on this. That minus sign, or that I should say logarithm properties, that minus sign can be put up as an exponent. The e and the ln, they just cancel and leave you with an x to the minus 1. And if you prefer, you can just write that as 1 over x. That would be also just fine, like so. Okay, so there's my integrating factor. So now I'm going to come up here and I'm going to create, just as you see right here, I'm going to create the derivative of the product right here of the integrating factor, which is 1 over x, times my unknown function, which in this moment is u. Right now, my unknown function is the u, so I'll be sure to write it as u here, okay? And then on the right-hand side, remember we have to have q of x times I of x, where, again, the q of x is this thing right here. I take that, we multiply it by the I of x, which is 1 over x. So 4x squared ln of x divided by x just leaves me with 4x ln of x. Okay, so that's what we have so far. And I'm pulling up my screen again because, of course, I'm going to give you a table of integrals. In the special handouts folder, there is an annihilators and integrals table. And something like x ln of x, that's not something I'm going to be asking you to do on the exam. It's a little too much, in my opinion. So I know this is hard to read, but you'll have this at close range when you take the exam. If I use number 8 on the table of integrals, so I'm going to use number 8 now on the table. I can integrate that right-hand side. So remember, the next step is to integrate both sides. When I integrate on the left side, I just get rid of the derivative. So I'll have a 1 over x times u. When I integrate on the right side, I'm going to pull the 4 out as a constant. And then the rest of it is the integral of x ln of x, which is in this table under number 8. I know it's really hard to read, but you have to plug in k equals 1 into that. And I can read it good enough to write it down for you for now. We don't have to worry about it too much. But what you're going to get here, guys, is x squared over 4. Okay, so if k is equal to 1, then I'm going to get x squared over 4 times the quantity 2 ln of x minus 1. Oh, I forgot to make a comment earlier. When we did this integrating factor here, notice that when I did the antiderivative of 1 over x, I did not add a plus c on the end of this. You do not need to do that for integrating factors because you just need to find one acceptable integrating factor. So I basically just chose c to be 0 right here. However, now in this moment, when I'm actually close to solving for u, I do need to get the general solution for u. So I'm going to add a plus c onto the right-hand side of that. Okay? Is everybody with me? Like going at a decent pace? Yeah, Shay?
The 1 is not inside the ln, right?
Right. This is 2 ln of x with a minus 1 subtracted from it. Yeah, that's a good point. And again, I'm just using this thing right here on the table, which is a little bit hard to read. We okay? All right, so then I got to solve for u. To solve for u, I just need to multiply through by x. So u would be equal to, actually, so yeah, okay. I guess I could just I'll put the x here, 4x. There's several ways to simplify this algebra, but I'm not gonna be looking for you guys to spend a lot of time simplifying a lot of algebra. But technically, the x gets multiplied by everything on the right side, including the c. Okay, so we'd have something like that. You could call that good if you wanted to. By the way, c times x, it's not still c, right? The x is a variable now, so I would not want, sometimes people wonder, well, can I change that to like c1? No, you can't, because the x is actually a variable. Now, if it had been something like e to the c, that's a constant, because e is constant, c is constant. You wanna call that c1, totally fine, right? Or if it was c plus 5, that's a constant, you add 5 to it, it's still a constant, so that could be a c. But if I have c times x, I need to just leave it as c times x. When in doubt, just leave it, because I'm not gonna be expecting you or requiring you to clean something like that up. If you just have a c times x there, that's good enough for me. So this is fine for you, or am I done? Why am I not done? I have to give my final answer in terms of y. As of this moment, I have u. If I want to solve for y, this box right here is going to help me do that. You can see that if you wanted to solve for y, you would need to take the 3/2 power of both sides, right? Y to the 2/3, if I raise that to the 3/2, I'll solve for y. So the y is just going to be this entire thing to the 3/2 power, okay? So I would probably do that and then just start filling it in. 4x times the quantity x squared over 4 times the quantity 2 ln of x minus 1 plus c times x. And I should have had a bracket right there. And I think that should do it. Does that look okay? So what we just did right here, guys, is we reviewed Bernoulli equations, but we also reviewed linear ones. Because Bernoulli equations always turn into linear equations. And so it's good to practice those Bernoulli problems, because it gives you kind of a double shot of practice that way. Everybody okay? Is this making sense enough? Questions here? Okay, all right. Pretty sure if you look at my sample midterms, you're gonna see some Bernoulli examples, but, and again, don't freak out if you're looking at this like, oh my gosh, I don't think I could do this. Of course, it's been a while, so just getting it back in our heads is gonna take a little bit of practice. So try not to worry too much about that. Okay, I'm gonna move on to another problem unless there's any question here. Okay, let me get this off the screen, and I'm gonna use the next board over a little bit. Let's do another topic here. I'm the linear algebra guy. I can't just do differential equations. Got to do some linear algebra too. Let's try another example. I'll call this one's number 2. And here's what I'm going to do, guys. I'm going to let S be equal to the set of A plus, well, actually, let's do it this way. I'm going to say P of X in P3 of R such that P of 3 is equal to 0 and P prime of 4 is equal to 0. So this is actually not off of any of the handouts. I'm just making this one up right now from scratch. Okay, because I just think this is a good problem. What I would like to do is I would like to do a couple things. Part A, I would like to show that S is a subspace of P3 of R. So I'd like to show that it is a subspace of P3 of R. One of the first things that we usually do with this is we would do what's called a zero vector check. And if the question had said to decide if S is a subspace or not, I probably would do it. Because if the zero vector check fails, let's just remember, what does this mean again? The zero vector check just says if 0 is not in S, then S is not a subspace. So this is This is a fast way of checking that S is not a subspace. So if this question had said, decide if S is a subspace or not, I probably would start with that, because if the zero vector check fails, meaning that if zero is not in the set, then we're already done. It's already game over. It's not a subspace, and we can very quickly move on. In this case, I don't really need to bother with the zero vector check, because they're telling us to show that S is a subspace, which means that you already know that it's gonna pass the zero vector check, and so we don't need to waste our time with it. Does anybody remember the main things we have to check, though, if something is going to be a subspace?
Closure under addition and closure under multiplication.
Nice. We have two things, right? There's two operations in a vector space: closure under addition and closure under scalar multiplication. Exactly. So that's what we're going to need to do: closure under addition and closure under scalar multiplication. I'll start with the addition first. Before I do that, before I leave the zero vector check behind, one quick comment here. What is the zero vector in this problem? We have to look at our universe, P3 of R, and we have to ask ourselves, what would have been the zero vector there? So in this context, maybe you don't really need this for this problem, but just so we have it kind of on the side here. What the zero vector would be, guys, we're talking about cubic polynomials. The zero vector would look like this: 0x cubed plus 0x squared plus 0x plus 0. That is your zero vector in this universe. All of the coefficients are 0, but it looks like the form of something in P3 of R, right? When I write it like that. And so then the question would be, okay, if I plug in 3 for x, do I get 0? You come over here, if I put in 3 everywhere I see an x, well, the whole thing adds up to 0, definitely. And even if I take the derivative of this thing, right, the derivative of this polynomial is still going to be just 0, right? You use the power rule, pull things down, plug 0 in for x, or sorry, plug 4 in for x into the derivative, you're still going to get 0. So just in case you're wondering, that's how the zero vector check would have looked. But we don't really need to do it here, because we know that it's going to pass the zero vector check. Right? Okay, so let's check the closure under addition here. To do this, we have to invent some notation. We have to decide what we want to use for our notation. I need two vectors from S to begin with that I'm hoping to add together. So we can call them whatever we want. We could say, let P of x, comma, Q of x be elements of S. And what this would mean is, well, if they are elements of S, we just have to look at here. This is the condition for something to be in S. So if P of x and Q of x are in S, then we can write down what that. So I'm not ready to add them together yet. Ultimately, I'm going to add them together, but before I do that, I just want to write down what we know. P of 3 equals 0, P prime of 4 equals 0, Q of 3 equals 0, Q prime of 4 equals 0. All of that information is assumed here as part of the assumption. Okay, so we get all of those conditions, and now I want to add them together. So we will now consider, I'll just write it this way, consider P of x plus Q of x. I'm checking for the closure under addition. And the question is, well, what happens when you put in 3 into P of x plus Q of x? So I'm going to now plug in this. I'm going to use the same condition. I'm going to test whether when I put 3 in as an input, do I get 0? Well, let's check it out. So if we do P of 3 plus Q of 3, oh, well, that's very easy, because we were already told that P of 3 is 0 and Q of 3 is 0. That's given, basically. So this is 0 plus 0, which is equal to 0. I'm going to just put a little check next to that. Okay, and then I've got to also check that if I do the same. Actually, if you don't mind, I'm going to back up a step here. Technically, I should be writing P plus Q as a polynomial. that I'm plugging 3 into. I'll just add that on the left there. If you didn't write that down, I probably wouldn't be too upset, but it just makes it a little more clear. P plus Q of 3 is equal to 0. The other thing I need to check is what about the derivative of P plus Q evaluated at 4? And again, we all know that derivatives respect addition, so I can think of that as P prime of 4 plus Q prime of 4. And again, we were already given that P prime of 4 is 0, and we were already given that Q prime of 4 is 0, so of course, add that together, we get 0. All of that confirms that P plus Q satisfies the membership condition for S. And so don't forget though, that there is a punchline that brings out my red pen if it's missing. And that is that you need to tell me at the very end, guys, that yes, P plus Q is an element of S. I do want to see that to wrap it up. Basically, that kind of puts a bow on it and wraps up that part of the verification. It's closed under addition. So far, so good? Remember doing this? It's been a while. This is always everybody's favorite thing when this is like the moment when Math 250B starts to not feel like a calculus class anymore. Everybody's like, what is Dr. Inman talking about? Yeah, so this was when we started into subspaces. Now, we also have the closure under scalar multiplication, so I'm gonna make a separate little section here for that. Bring the camera in here a little closer. If you remember, the way I like to do this is I like to just say, let K be an element of the real numbers. So I grab a scalar, which I'm gonna call K. And then I usually call it K. Of course, you can call it anything you want. And then I'm just gonna say P of X as above. So I don't wanna write out everything about P of X again. So I'll just say, just use everything about it that we had already written down from above. And now I'm going to look at K times P, right? So then we're gonna take K times P and we're gonna plug 3 into it. And I'll just go ahead and jump to the next line as well. We're gonna take the derivative of K times P and plug 4 into that. And we just wanna check that everything works out. We're supposed to get 0 in both places, right? Okay, well, we all probably know that when you have a constant times a function, that constant can just be pulled out. So the K comes outside. And so K times P of 3, that's just K times 0, because remember, P of 3 is equal to 0, and that equals 0. Put a little check on that. Okay, so K times P of 3 equals 0, and then the derivative, same thing. Derivatives respect scalar multiplication, so I can pull the K out of the derivative there, and it's just K times the derivative of P. Well, that becomes K times 0. This is also still equal to 0, again, because P prime of 4 is 0. Okay, great, so both of those things are true. I'm not gonna forget the punchline. The punchline is that K times P is in S. Okay, so that does it. That checks it. We've checked the closure under addition and the closure under scalar multiplication. Any questions on that? It's been a while since we've done one of those.
You don't have to queue for multiplication.
Right, when you're doing the scalar multiplication, you only need one vector and one scalar, so you could just pick the P of X, and that's all you have to do. Yeah, very good. Excellent point. Okay, I have a part B to this question. Let me come back over here. I'm gonna erase this first board and ask you, because guys, once something is a subspace, the floodgates open up with all kinds of further questions. What's the dimension of it? What's a basis for it? And can you verify all of that? So let's try to find a basis and dimension for S. All right, see if we can do it. So part B is going to be to find a basis and dimension for S. Okay, see if we can find a basis and a dimension for S. So again, S. In case some of you are following along on the video of this, let me just rewrite over here what S is so that it's easy to see it again. P of 3 equals 0 and P prime of 4 is equal to 0. Okay, so we have a subspace. We already checked that part. So now I want to find a basis and a dimension. Anybody have any thoughts about how we would begin to do this part of it? I guess I'll just remind you again, also a basis, remember a basis is sort of two things. That it has to be a spanning set that is also Li, right? So it's a spanning set that's also Li. So we could kind of dumb it down for a minute and say, well, how do we even get a spanning set for S? A spanning set, we spent a good chunk of a lecture on this topic. And there's even a handout about this a 3-page handout that I made a couple years ago that spells it out in 3 pages with a lot of examples. But if I ask you to find a spanning set for something, really what you need to do is a 3-step process. Write down maybe I should write it down. So we're gonna write, this is the most important step, is this first one right here, which is to write the form of a vector in S. Using variables. So you have to use some variables to do that. So you write down the form of any vector that's in the set. Once you've got the form down, does anybody remember what the second step was?
Bust out the variables.
That's it. Awesome. Bust out the variables that are showing up in that form. We bust out the variables, and boy, we did a lot of these. We did a lot of these back in the homework in chapter 4. Bust out the variables, and then thirdly, anybody remember the third step?
Find the basis of that bust out variables.
I'm sorry?
Find the basis of that.
Yeah, from the busted out form, you just make a list of the vectors that are showing up in that form. At that point, you're pretty much ready to just write down the answer. Yeah, so it's make a list of the vectors that remain. Okay, so boy, we did a lot of these. Do you remember the homework problem? It was the 2x2 matrices where the 4 entries add up to 0. So you had to do something like, okay, A and B and C, and then, okay, if I need them to all add up to 0, then this has to be the negative of A plus B plus C. You remember that problem? You take this form and then you bust out the A, you bust out the B, and you bust out the C. Actually, you did even more than that. In the group work, I did it the same problem for you with 3x3 matrices. And so you actually had not just 3 variables that you had to bust out, there were actually 8 of them. So I don't know if you remember that this was on group work number 8. So some of you, I imagine, might want to look at some of these group works again. We had to write down like the general form of a 3x3 matrix where the entries all add up to 0, and we had to do some huge thing like this. Alright, so this takes us back to somewhere in March probably, when we were kind of doing this kind of thing. So you would write down this form and then bust out the variables, and you get 8 basis vectors here. So I can ask this kind of question, guys, with matrices. In the current problem, we're going to do it with polynomials. It could be with traditional physics vectors. It could really even be with calculus functions. It doesn't really matter. It's the same 3-step process. Yeah, so let's, I won't go back and redo these examples any further because I hope I've triggered your memory about them and you can look those up. Let's do the one that's on the board though. Let's find a basis and dimension for this type of subspace. So I have to start with step 1 now. So now I'm going to try and do the solution. I'm going to try to follow along my little cheat sheet here. The first step is to write the form of a vector in S. Does anybody know a vector in S is going to be P of X? Does anybody have an idea how to get started on writing down that form?
A is cubed, plus B is squared, plus C is plus D.
Exactly, there's nowhere else to start than probably doing this, right? AX cubed plus BX squared plus CX plus D. Now, I would argue though, that this is not the form of something in S quite yet. It's definitely a step in the right direction. But this would be the form AX cubed plus BX squared plus CX plus D. That would be the form of something in P3 of R. And if I bust the variables out of this right now, all I'm gonna get is my standard basis for P3 of R, which would be 1, x squared, and x cubed. And if I do that, if I bust out the variables now, I'm completely ignoring the conditions that are over here. So I need to use this, I need to get this into the game a little bit, right? So let's do the following, guys, to help us with this. This is not really the end of step 1 yet. I need to plug in 3 into this polynomial and just see what I get. So P of 3, so if I plug in a 3 everywhere I see an x, I'm gonna get 27a plus 9b plus 3c plus d, and I'm going to set that one equal to 0. Okay. Now, I need a little bit more room here. We are also going to need to work with the derivative of p of x because there's a condition involving the derivative here. If I take the derivative of this thing, I'm going to get 3ax squared plus 2bx plus c. That's just the derivative of the original p of x. And I'm now going to plug in, I'll do it down here. I'll plug in 4 into the derivative equation. So now I'm plugging in 4 because that's what the set S involved. So I plug in 4 everywhere I see an x here. So this is 4 squared, which is 16. I multiply it by 3, I end up getting 48a. And then I have a 4 here times 2, that's 8b. And then plus c. That's also equal to 0. And what you've created, guys, are some equations that will put conditions on A, B, C, and D. And we can actually throw this into a matrix like we do everything in this class. We can make a matrix here, 27, 9, 3, 1, augmented with 0. And then on the second row, 48, 8, 1, and 0. So the unknowns in this little system that I'm writing down on the board, those unknowns would be A and B and C and D, like so. Okay. Guys, I confess to you that I've made this problem up on the fly. So I didn't promise this was going to be an easy matrix. On the test, I'll be much more careful that the numbers are nice. You can see I don't like how the 47, the 27 and the 48 are sitting next to each other. EROs with that doesn't sound so good. Actually, what I would probably do is just multiply the first row through by 1 over 27 as a starter. So I would probably get a pivot of a 1 here in the upper left corner. Okay, so let me move my camera just a little bit. I've got to do a little bit of work on this augmented matrix to try to solve for A, B, C, and D. So I'm going to divide through by 27 on the first row of this matrix. So you're just going to have to trust me on this. I'm going to try my best not to make crazy computations for you guys to have to do this week. The second row, I'm going to leave it the same. Oops, I'm going to leave it the same. 48, 8, 1, 0, and 0. Okay, and now I have to multiply the first row by negative 48 and add it to the second row. So A12 of negative 48. Oh, very soon I'm going to get to take 3 months off from doing this. And then I'll get to start all over again. So negative 48 times the first row added to the second row. What's negative 48 times 1/3? 16? So that's negative 16 added to 8 makes negative 8. Negative 48 over 9 is the same as negative 16 over 3. Simplifying fractions. Negative 16 over 3, I'm gonna add that to 3 over 3. And it comes out to negative 13 over 3. And negative 48 over 27 is the same as negative 16 over 9, which I have to add to 0. I'll get negative 16 over 9. And fortunately, the last entry will still be 0. I'll put my little pivot here. And this is close to row echelon form. As you know, technically the pivots need to be 1s, but I'm just gonna stop with my EROs right here. Here's A, here's B, here's C, and here's D. And notice that we have 2 free variables, which are C and D. So I'm gonna call them, my favorite letters are usually R and T, because I usually don't confuse them with anything else very easily. So these are free. C and D are free, and now I have to do the hard work of solving for B and then for A. So I'm gonna need just a little more room to back substitute. So from this second row, right, negative 8B minus 13/3 of C minus 16/9 of D is supposed to equal 0. Again, I'm sorry, it's kind of a messy calculation. That's just because I decided to wing it. So I'm gonna move the 8B to the other side really quickly. I'll leave everything else the same. If you don't want to take all of these notes and just want to get the big picture of it, we'll get to an answer here in a minute that you guys could just copy down. And so I'll divide through by 8 to get my expression for B. So B is going to be negative 13 over 24C minus 2/9 of D. So far, so good. So far, so good, but I have to figure out A. Yeah. So to solve for A, this first row tells me that A plus 1/3 of B plus 1/9 of C plus 1/27 of D is equal to 0. That's the first row of my matrix. And so I have to solve for A. A is going to be negative 1/3 of B, but I'm going to put B in right now. Negative 13/24 of C minus 2/9 of D. Actually, I could be using my R and T at this moment as well. It doesn't actually matter. So at this moment, I'm using the C and D for that. So negative 1/3 of B, and then I have to do minus 1/9 of C, and then minus 1/27 of D. So the only question left is how bad is this going to be to simplify these fractions? Let's put the C terms together. Negative 13 over 72. And this is actually negative 8 over 72. 1/9 is the same as 8 over 72. So negative 13 over 72 minus 8 over 72 is negative 21 over 72 times C. Okay, and then what about the D coefficient? 2/27 of D, right? This is 2 over 3 times 9. 2 over 27D minus 1 over 27D. That should be plus 1 over 27D. You know what? I'm just gonna forget the R and the T. It's not really necessary to change those letters, and it's messy enough that I don't really want to do it. So we'll just leave the C and the D as the free variables. That's totally okay. Guys, we are still on the step 1 of this process. Find the form of the vectors in S, but you know what? I'm now ready to write it down. Because, guys, what is it? P of X equals AX cubed, but here's what A is. Actually, can this be reduced? Yeah, I can cut out factors of 3. So 7 over 24. So P of X is negative 7 over 24 C plus 1/27 of D times X cubed, right? That's the A value times X cubed. And then the B coefficient is negative 13/24 of C minus 2/9 of D, that's times x squared. And then C and D were free, so they don't have to be replaced at all. We can just write the last two terms as CX plus D. Okay, so that's what we would have there. And that's the end of step one. That's writing the form of a polynomial in S. Are we okay? Don't be intimidated by the messy calculation part of it. The main thing is, do you follow like the process? Right, I had to incorporate the given conditions here. P of 3 equals 0 and P prime of 4 equals 0. Every time I did that, I don't know if you noticed this, we went from 4 variables down to 2. How come? Because each extra condition that I give you constrains my set S by one more sort of degree of freedom, right? So you lose a free variable every time you add a constraint up there. If I made another constraint right now, we'd lose another one of those 2 free variables, we'd be down to only 1. Okay? Anyway, so that's step 1. Now step 2 is to bust out the variables, of which now I only have the C and the D. Just to remind you, with polynomials, the x is not a variable. The x is a part of the vector. It's sort of a piece of the structure of the object in the vector space. So the x is not what you're busting out. You're busting out the C's and the D's. So let's do that right here. So this is now sort of the step 2 of that 3-step process that I reviewed over there. So I pull out the C. And when I pull out the C, what I'm gonna have is -7/24 times x cubed. And then minus 13/24 times x squared. And plus x. Okay, so everywhere I see a C, I have to factor it out from every term that it appears in. And then I go back and I do the same thing with D. Okay, I do the same thing with D, and I have 1/27 times x cubed minus 2/9 of x squared, and then a plus 1 on the end of it. Okay, and so that's step 2, and it has left me with these 2 polynomials. Question?
If obviously the exam is gonna be as messy as this kind of first part was.
I hope not.
If you were to
I
have
haven't
left
written it
it,
yet, so I don't know, it could be worse.
if you were to have left it as R and T, would it just be R and T substituted for C and D over here?
Yeah, you would just have an R here and a T here. I couldn't really care less. It's just a choice of what free variables you're using. Yeah, that's a good question. Okay, so we get that, and then finally, step 3 is to make our list. So step 3. What we do here, guys, is we drop off, and some people I've noticed are not really doing this, which is to get the constants out of this list. So there should not be, you should not be carrying the C and the D into this list that I'm making. So I just write down the first polynomial from the parentheses here, and then I just write down the second polynomial from the parentheses here. Looks something like that, and I just turn that into a list. By the way, you probably wouldn't want to do it if it was this messy, but technically speaking, if you plug in 3 for x into either one of these, you better get 0. This one's not too hard. If you take 3 cubed, you get 27. So this is a 1 minus 3 squared times 2/9 is minus 2, and then plus 1. So 1 minus 2 plus 1, that is 0. And this one, hopefully, if I didn't make a mistake, this would be the same way. Keep in mind, if you were to fumble up some number here and you ended up, obviously, then you wouldn't have the right thing over here. But I would not recommend erasing everything and like turning in nothing, right? You should just keep working it through, because if you get something here that's even off a little bit because of some, maybe you made an ERO error, I don't have to like take off much points at all. Maybe I wouldn't even take off any points, or at most maybe 1 point, because the ERO part of this is really not the main point, right? It's not really what I'm mostly interested in. So this would be your list. Now, is that a basis though? I've explained that that's a spanning set. But is it actually going to be a basis and not just a spanning set?
You have to check with me.
So linear independence would be the other piece of that definition for a basis. Do you think these are gonna be linearly independent? The answer is yes, and we can give a pretty quick yes on that. These are Li, and what is the reason?
Because there's two, they're not scalar multiples of each other.
They are not scalar multiples of each other. Pretty sure of that, right? So they are Li since they are not scalar multiples. I do still, from time to time, see people sort of over extending that definition or that property. This not scalar multiples thing works great if there's two vectors only. Okay, so remember, if there's more than two vectors, if there were three vectors here, you can't say that they're Li because they're not scalar multiples. You can have three vectors, all of which are mutually not scalar multiples of any of the others, but which are still LD, actually. So when there's three or more vectors, we can't use the scalar multiples condition. If there were three or more vectors, what would you maybe do to convince me that they're Li? Yeah, I could actually use the Wronskian, which actually in chapter 4, we didn't really have it back then, but we could use it here. We could say, all right, I'm gonna put these into a matrix. I'm gonna take enough derivatives to make it into a square matrix. I'm gonna try to plug in a number for X that makes the Wronskian not 0. If you can find even one number to plug into that, what would it be, a 2x2 determinant, such that it's not 0, then they're Li by that Wronskian test. So you could definitely do that. You could also do it from the definition of Li, but that's pretty tedious. You'd have to take, you know, a linear combination of your vectors, set it equal to 0, and prove that all of the scalars of that combination are 0. And that would be a fair bit of work as well. So these are Li, they are a spanning set, so this is my basis. And if that's the basis, then what's the dimension of S? 2. Exactly. You can usually just write that down as an afterthought. It doesn't take a lot of work to come up with the basis at that point. Okay, fantastic. Comments, questions? Seems okay? That problem took a while, but that's okay. This is we covered a lot of ground here, right? Subspaces, checking for finding and checking a basis, remembering kind of how that process works. Very likely. So we've only done 2 problems so far, but the 2 problems that we've done have had a lot of content to them, and they're both probably very likely types of questions I might ask you. So I'm trying to do things that are mainstream, right? Trying to shoot straight down the center with this thing right now and try to hit the highlights first before I go any further. So another topic that I think we should review, because it's been a while, is inner products. So I would like to do an example of that as well. And maybe we can start with that here. So let's do number 3, unless there's anything else about this, because there was a lot here.
We just kept, CNDS free variables, but we didn't use R.
Right, if you used R and T, that would be fine, yeah. I actually, sometimes students will ask me, why are you introducing these new letters? You can just use the old ones, and that is true. But I always, especially when people are first learning it, I like to kind of always change the letters to R, S, and T, because it gets people in the habit and they recognize those letters, like, oh, I'm using free variables now. So here we are at the final exam, end of the semester. I feel a little more comfortable saying, all right, we know that C and D work as free variables just as well as R and T. Yeah, good comment. Okay, so let's practice something on inner products here. So let's let V be equal to P2 of R. So that's my vector space. Remember that if I'm going to ask you about inner products, I have to give you a formula. The only exception to that is if the vector space was Rn and I don't say any word about what the inner product is, you can assume that we're using the regular dot product in that case. So I only bring that up because in the book, that's what they do. If the vector space is Rn and there's no mention about the inner product, is because you're just supposed to assume that it's the standard dot product. But in any other vector space, including this one, I have to provide you with an inner product. So I'm gonna do that now. I'm going to define an inner product here of ax squared plus bx plus c. That's a quadratic function. And then dx squared plus ex plus f. So I take two polynomials and I'm going to give you this formula. And the formula is going to be a times f plus b times e plus c times d. So I'm defining that, and then I'm gonna ask the question, is this formula a valid inner product on V? Yeah, so it might not be a terrible idea to take a minute and review the axioms for an inner product. There's like 4 properties that an inner product has to satisfy, and that's usually with this kind of question, you have to think about those axioms and whether they would work for the formula that you've been given, right? So that's the way this works. So let me just recall, before I actually solve this problem, I'm gonna do a very quick crash course. Again, if you watch that 30-minute review of chapters 1 through 5 in that video that I showed you from the website, it'll give you an overview of all these concepts, but it won't be with any examples. It's just be an overview of the actual material. Yeah.
What chapter it is?
Oh, this topic is chapter 5. Yeah, chapter 5. And this was mostly covered on the second exam. So this is pretty much dead center in the middle of the semester. Okay, so let me just recall here that the axioms are, so there's 4 of them, inner product axioms. And you're gonna, to answer a question like this, you have to know those axioms. So the first one is that if you take the inner product of any vector with itself, the answer is always at least 0. And it can only be equal to 0. It would be equal to 0 only if you were actually working with the 0 vector itself. If it was any other vector, then you could not get 0. You'd have to get a strictly positive value, okay? One way that I always remember this axiom is if I remember the concept, and this is not part of the axioms, but you might remember one of the most important things that we do with inner products is we calculate norms of vectors. And if you remember the formula for the norm, it's the square root of the inner product of the vector with itself. This always reminds me that, oh, well, whatever's under that square root needs to be a positive value. So that's kind of a reminder that our axioms are going to have to be complying with that definition. So the inner product of any vector with itself should be at least 0. Okay, and then let's see, what else do we have? If we take the inner product of V with W, it should agree with the inner product with W with V. So I should be able to switch the order, and it makes no difference. Then the third one involves a constant. So the inner product of, I think I used a C for this just to be consistent with the book. So if I take a scalar multiple, C times V, and I calculate its inner product with W, I have to be able to pull the C out. Okay? In this axiom, the constant is sitting in the first slot of the notation. I will remind you that we talked about this at the time in chapter 5, that it's actually also true that if there's a constant in the second slot, it also must be factorable out. And so if you had a constant in both slots, they would actually both come out, right? So you'd have to be able to pull both of them out, first slot and second slot kind of independently. Yeah.
You pull them out, do you multiply them?
Yeah, you would. Yeah, exactly. So if there was if this was C times V, and then this was D times W, then you could pull the C and the D out and you'd have C times D. Times the inner product of V with W, but that's technically not the axiom. The axiom only addresses the first slot. But because of axiom 2, which allows you to switch the order of the two slots, you can actually pull constants out of either slot. Yeah, making some sense? There's a fourth axiom here. I hope we don't have to get into this one because it's kind of long to write it out when you're actually checking it. But if you take V1 plus V2 and you do the inner product of that with W, so now I'm going to do addition. If I have a plus sign in that first slot, well, I can factor that into two parts. The inner product of V1 with W plus the inner product of V2 with W, like so. Yeah, so in other words, the inner product actually respects it actually respects addition and scalar multiplication, much like a linear transformation has to respect addition and scalar multiplication. So that's kind of nice to see. Okay, so those are my axioms. I recommend that you kind of have these learned in this order. And that's because unless I give you a really pathological formula to work with, most of the time, these lower axioms, which are more algebra oriented, they usually will work out unless I really do something kind of bizarre with the formula that I give you. The first one is often the one that doesn't check out. Let's check it out now. For this formula in P2 of R, let's check out what happens. So now I'm going to go to the solution of this problem number 3. What happens when I take the inner product of a vector with itself? So in writing that down, I'm going to take ax squared plus bx plus c, and I'm going to take its inner product with itself, ax squared plus bx plus c. So the same vector going into both of the components of the inner product. And what this means is that where I had the D, E, and F in the formula, I now am replacing those with, respectively, with A, B, and C again. Okay, so let's just read off how it would go. A times F would turn into, what would that be? So A times F, that's this one times this one, right? So that's A times C, right? That'd be AC. And then B times E from the original formula, now in this notation, it's B times B, right? B squared, yeah? And then finally, the last term is supposed to be C times D. That's these two numbers that are right next to each other. So if I look over here, what's right next to each other is the C and the A. Oh, that's just another CA. I'm going to just put it in front with a 2. Okay, so that's what we get using the formula that we were provided with. Now, my question is that good? Like, is that okay to get that for an answer? Is it going to be always greater than or equal to 0? Or could that come out negative somehow? Remember, guys, if I tell you that all Saturdays are sunny, all it takes is one false Saturday. One Saturday that's not sunny, and the whole thing crumbles. The whole statement is wrong. So if you can even come up with an example, any choice of A, B, and C, you get to freely choose those variables. If you can make a clever choice of A and B and C that would make this fail, then the axiom would fail and it would be game over. It's not a valid inner product. Can we make that fail? I think we can. Yeah, let's try. Can somebody give me some numbers here? There's like going to be lots of answers. Somebody, go ahead, Chan.
-1, 1, and 1.
-1, 1, and 1. All right, let's just plug them in and see what we get. So if we try this example, 2 times -1 times 1, that's -2 plus 1 squared. That's -1, and that is less than 0. It does not satisfy the condition that it was supposed to be greater than 0. So specifically what we had here, I mean, I would probably just accept this as is, but just so we can see how it would look, what you're talking about is this polynomial specifically. Negative x squared plus x plus 1, inner product with itself, and it comes out less than 0. Yeah, so this first axiom, so this is now a no. This axiom here fails. And if one of the axioms fails, you do not have to proceed with the others. Okay, because all of the axioms would have to be true for it to really be a yes. And so if something is failing right away, well, more power to you, you're already done. Okay, and really if it fails, then there's really nothing else to ask. Like at this point, if it's not a valid inner product, then I can't ask you the kind of questions I normally will start asking you. I'll start asking you, oh, okay, so it's a valid inner product. Tell me the angle between these two vectors, or make a orthogonal set out of these vectors, right? Or what's the norm of this vector? I can't ask you any of those questions, right? I can't ask you about norms or angles or orthogonal sets or orthonormal sets. I can't do any of that unless I'm working with a valid inner product. So this is kind of a game over. It's a dead end as far as doing anything else. So since I want to do something else, maybe I need to come up with another formula that we can actually play a little bit better with. Okay, so let me come back over here and we'll just do another example. Any questions though on that so far? Some of this stuff kind of coming back a little bit. Well, I'm hoping that so far I've been mostly just reviewing from the first 5 chapters. I'm hoping that the stuff from the 3rd exam doesn't need as much time, although it's kind of each person individually has to decide that. Okay, so let's do another one. This is actually number 4. We're still going to talk about inner products again, because I want to do something where this actually does pan out. So again, on number 4, I'm going to take P2 of R for my vector space. And I'm going to define the inner product of ax squared plus bx plus c with dx squared plus ex plus f. This time I'm going to make it equal to a times d plus b times e plus c times f. So I've changed the formula just ever so slightly. I barely changed it at all. I basically just switched the position of the d and the f in the formula. And basically it's the same question, is that a valid inner product? So is this a valid inner product? Same question. And this time, if I write out the first axiom, so if I write out axiom 1 here, you can see that I've got, the inner product of ax squared plus bx plus c with itself. So I am doing exactly the same thing I did on the last example, but now I have a different formula. Now the formula says take the x squared coefficients and multiply them together. That would be a squared. And then take the middle coefficients of x, which is b times b, multiply those, we get b squared, right? And then the last term is c times f, which is literally just multiplying the constant terms. This time, we get that formula for the inner product of this vector with itself. And so, of course, this, as we all recognize, is just adding up some perfect squares. Cannot get a negative number from that. So this is definitely greater than or equal to 0. So we'll check on that one. It's definitely greater than or equal to 0. And there's only one way to have this thing come out to be equal to 0. This is equal. I'm doing the part. So remember, guys, there's a part in parentheses over here. Equals 0 only if b equals 0. So I'm just going to add that here, guys. Equals 0 only if a and b and c are all 0. And of course, if a and b and c are all 0, then your polynomial is literally the 0 vector, right? This is basically P of X equals 0 in that case. So that checks sort of the extra condition as well. That definitely checks it. So what do we have to do now? If it passes that axiom. One more time?
You can check the next one.
I have to go to the next axiom. Yeah, I have to go to axiom 2. Let me write it down. I may not, actually, what I've known to do on my exams is to let people choose. Instead of verifying all 4 of them, which could take half an hour, I might say, write down and choose 1 or 2 of them to do. Let's just do this one and then I'll probably call it good. So if we do, if we do axiom 2, we need to look at what happens if we do the inner product in the reverse order. So let's put the cx squared plus dx plus. Oh no, I'm sorry. It's dx squared. Sorry, I'm writing this wrong. Dx squared plus ex plus f, inner product with ax squared plus bx plus c. Yeah. Well, so if it's written like that, then to make it compatible with the notation of the formula, we would write dA plus EB plus FC. Agreed? So just, first coefficient times first coefficient, according to the way I wrote the formula, we put that as a D times A rather than A times D. But what can I do with this? I could just, right here, these are just numbers. These are just numbers, so I can, of course, just switch this. AD, I can switch to EB, and I can switch to the FC. I can just switch it around. Oh, and now what I have is the inner product. This is, of course, just the inner product of the original polynomials in the original order. So we can get right back to that immediately and kind of check that one off. Yeah. Kind of check that one off. You seen enough of this? Do you want me to keep going, or I will point out when you do the third axiom, I've used a C over here. I would recommend that if the C is already being used in the description of your inner product, you might pick a different letter like K. Pick some letter that has nothing to do with what's going on here and do that. But again, the rest of the axioms all follow through very easily. So axioms 3 and 4, anybody who wants to check those can do so. I've got the solutions to this typed up because this one is directly from my review packet. So I think I'll skip that because it's a little bit just mundane calculations. I want to get to a, so now I'm going to do a follow-up on this because this is a valid inner product. Let's put a yes here. Yeah, this is valid. And so now I can start asking you some other questions. So let me give you an example of what kind of question might come next. After I've got a valid inner product, the next question is probably going to be something like this. Follow up. Question. So here's a follow-up. Might be something like this. Find an orthogonal basis for, I'm going to call it S, and S is going to be the span of the following polynomials. 1 minus 2x plus 2x squared. And my second vector is going to be 2 minus x squared. You could try something like that. Okay. Yeah, so I think I like this. What topic does this have to do with? What the buzzword comes into your mind when somebody's asking you to find an orthogonal basis? Yeah, if you remember, again, we're still talking about something that happened before spring break. So I know it's not something we've done a lot recently, but this would require the Gram-Schmidt process. We have what I will label as V1 and V2. Those are my original starting vectors. And from that, I'm now going to need to replace them. I'll just remind you that we're going to replace these with what are called W1 and W2. And there are formulas for those that I'm going to give you. So don't worry about this too much, but the main thing here is to recognize that this problem is going to use the Gram-Schmidt process. And if you just wrote that down and that's all you had time for, and it's like, okay, I'm just gonna write this down. I can give you credit for knowing what is the right tool to pull out of the box to do the problem, even if you didn't do it. So write this down. Just put as many words down as you think of as you go along, because that's how you get partial credit. Partial credit adds up. It really does. Okay, so we're gonna do the Gram-Schmidt process. I'll just remind you how that works. There's W1, which is V1. So there's not much to this. 1 minus 2x plus 2x squared, that's your first vector in your list. So that's easy. Where the work comes into it is with W2, and I will remind you the formula. Again, you don't need to know this one because I'll just give this to you. But the formula is V2 minus the inner product of V2 with W1 divided by the norm of W1 squared. All of that times W1. So it would look something like that. Okie dokie. So to really finish this off, we just need to do a couple of calculations here. This is just a number, right? This is a fraction. The top is a number, the bottom is a number, and you're calculating them using this formula, right? We just verified this formula. We're still using, guys, we're still using the inner product formula from the first part of this question. So let's just do these as little side calculations, right? So this is going to be the inner product of V2 with W1. Let's start by working this much out. And so that would be the inner product of 2 minus x squared with W1, which is 1 minus 2x plus 2x squared. Okay, and how does the formula work? Well, we have the box formula over there. A times D is 2. B times E is actually -1 times -2, which is also 2. And then plus C times F, which is -1 times 2, which is -2. So you add all of that together and you get 2. Okay, so that's the numerator of my fraction that I'm working on right here. The denominator is another calculation. Remember, this is very computational. Once you remember how it works, this is not as conceptually demanding as maybe some of the other things. This one is just the inner product of W1 with itself. So in order to do that, I have to take the inner product of 1 minus 2x plus 2x squared with itself. Okay, so I'm just going to write it down twice. And now I just go use the formula here, 1 times 1, which is 1 squared. And then -2 times -2, which is -2 squared. And then 2 times 2, which is 2 squared. And if we add all of that together, we should get 9, I think. 1 plus 4 plus 4. Okay, so we have a 2 and a 9, and that's what goes in down here. So what is W2? Let's just put it on another line here. W2 would be V2. I'm going to just recopy what V2 is. That's the V2 that we started with. And then minus 2 over 9 times W1. And W1 is 1 minus 2x plus 2x squared. Okay. That look okay? I would almost certainly accept it this way, although it's not simplified. I have a 2 and I can subtract 2/9 from that. So I will just do it just so you have something to look at. I would get W2 to be 16 over 9. And then the x coefficient, let's see. Here I have 4/9 of x, and I'm going to subtract an x from that. that turns into negative 5/9 of x. And then finally, the x squared term, I have negative 4/9 of x squared and another minus x squared. And that's actually negative 13/9 of x squared. Okay, so those would be the calculations that I have to do here to come up with the answer. And so I should probably, like, I would probably, again, I'd probably give all this full credit, but just so I don't like to write stuff down that isn't like, I hold myself to a very high standard. I have to actually write the answer. So the answer should be written as a set where I write down W1. W1 is 1 minus 2x plus 2x squared. And then I write down W2, which is 16/9 minus 5/9 of x minus 13/9 of x squared. That look okay? If you take the inner product of these two vectors, you should now get 0. So if I take 1 times 16/9 plus negative 2 times negative 5/9 plus 2 times negative 13/9, I would hope that that is 0. Yeah. Also, another question you might wonder is, well, can I just get rid of these fractions? Like, can I take the second vector and multiply it through by 9? And the answer is absolutely. If I take two vectors that are orthogonal and I decide I'm going to scale one of them up by 9 markers, I multiply it up by a factor of 9, they're still orthogonal. Right? This is still an orthogonal basis. So there's no reason you have to keep the denominators here. I mean, you can, it's not a problem. I'm leaving them the way they are, but you wouldn't have to. You could get rid of those fractions if you wanted to.
For non-true radical,
Remember that we're doing the square of the norm here. So if you remember there's the radical comes in, if I want to know the norm of V, it's the square root of the inner product of V with itself. But the minute that you put a squared on the norm, which is part of the formula here, then the square root goes away on the other side. It's a good question. Guys, also just to remind you to be really careful to read these questions closely. This is asking for an orthogonal basis. There is another related concept, which I imagine you remember, which is the idea of an orthonormal basis. So if I asked you for an orthonormal basis here, which by the way, I don't think I did that on the midterm. But if I asked you for an orthonormal basis, you would now need to take both of these, you would do everything the same, right? Up to this point, you just do exactly the same thing, but you would not quite be done yet, because if I ask you for an orthonormal basis, you have to divide each vector by its norm, right? So for example, this first vector would need to be divided through by its norm. I already know what it is, because the square of its norm was 9. So this would be dividing through by 3 right here to make it normalized. Again, putting scalar multiples on orthogonal vectors preserves them as still orthogonal vectors. No problem with that, right? So in this case, if I divide this first vector 3 by 3, I'm not losing the orthogonality of those vectors, but I am making this into a unit vector. So remember that the way that you normalize a vector, right? The way you make a unit vector is you take your vector and you divide it by whatever its norm is. Okay, so at this moment, I would have to then find the norm of this vector here. That's a little more work than I think it's really worth right now, in terms of calculations. But I just want to caution you, be very careful, guys, whether I'm asking for an orthogonal set versus an orthonormal set, because there is a slight difference. Okay? But yeah, if you see questions like this, find an orthogonal or an orthonormal basis for something, you want to be thinking about the Gram-Schmidt process. Those formulas are going to be on the front of the test, which you'll be able to use. Questions? Everybody good so far? Okay, let's do another example. That was number 4, okay. Another example here. I'm gonna go till 6. Back when I was a grad student, I was like much younger and more energy, I guess. Can you imagine me with more energy? Back in the day, I had more energy. I would do these review sessions, and this is when I was doing my PhD up in Berkeley. I would do these study sessions. I wasn't the professor either. I was just the TA. So I would just show up to do these sessions, and they kind of became legendary. Because they would go for hours on end. And so, and not only that, so then I had just like a small group. Imagine every person in this campus who's taking 250B right now, not just my students, the ones taking other professors too. They would, of course, get wind of this, that, you know, Scott Annan is going to be doing a review session for this class. And, you know, it will go for hours. You can learn so much. And so I started having these students from other professors who would just start showing up. And I didn't have enough room to do the session. I had to like start reserving an auditorium for these things. And we would like start at like lunchtime, and it would be fine. I'd have lunch before, and then it'd be like dinner time, and we were still going. And I said, well, I guess we'll take a break and come back. And so we did that. Everybody went off to have dinner, and everybody came back. And I was sort of like, I really didn't think you guys were going to come back after dinner. And they said, well, but you're going to show us some more problems. I didn't even know what was on the test. So I wasn't the professor. The professor was writing the exam. I was just trying to help out. And I finally, like 2 hours later, I was like, so if I stop doing problems, will you guys all go home? And they finally, I think they all wanted to go home at that point, and so did I, to be honest with you. And I just said, okay, we're not doing any more problems. So I stopped. But yeah, they would go forever, like.
I'll ask my friend at Berkeley if that happens.
What's that?
I'll ask my friends at Berkeley.
Yeah, no, it's amazing how, but I could handle it back then. I don't think I could go for more than, I could probably do a 4-hour session without doing too badly. I mean, after all, I've been teaching 4 hours back to back all semester. But I'm not gonna put you through 4 hours because I wanna have dinner and I wanna come back for my office hours. So I am gonna stop kind of on time today, and I am gonna tell you right now, we are definitely not covered everything. You probably know that. I'm just hitting some, you know, pinch points of things that I think are good to go over, but it's definitely not everything. So let's do another problem though, that would be helpful, I think, I hope, which would be the following. I'm gonna let V be equal to P3 of R again. I guess I'm on a polynomials kick today. So let's do polynomials here. And then I'm going to let S be equal to the set of, and I'm gonna make some polynomials now, guys. 1 plus X plus 3X squared plus 3X cubed, comma, X minus X squared, comma, I'm sorry, that's X plus X squared, X plus X squared. And then the next one is 2 minus X plus X cubed, and then comma, and then -3 plus 6X plus 6X squared plus X cubed. Okay, so we take that set, and I'm gonna ask you the following question. Is S Li spanning set for V both or neither? Okay. Yeah, so we could ask this one, right? We could ask this question. Is it Li a spanning set both or neither? Any thoughts about maybe what to do first?
Choice.
Even before we, yeah, of course, eventually we're gonna find a matrix showing up here, but what would be like the first thing off the top of my head? Yeah, Bergen?
So we could take the dimension of P3R and then look at the amount of vectors.
Yeah, you remember how we kind of always compared, like, what's the dimension of V compared to like how many vectors did they give us? So let's just get that written down first. What is the dimension of P3 of R, by the way?
4.
Okay, so remember Pn of R is always dimension of n plus one. So you add one to whatever the base dimension is. And then I was usually calling this K. K was supposed to be representing the number of vectors that's given. How many vectors are given here? Four, okay. So in this case, they're equal. So again, writing all this down, you get partial credit as you go. So put it all down for me. In the case when K matches the dimension, does anybody remember from my beautiful little table where I had the cases? That we can cross off two of the wrong answers immediately. What are the answers that, well, what are the possible answers based on this information? Both or neither, exactly. So it's not going to be Li alone, and it's not going to be a spanning set alone. It's going to be both or neither. Now I have to tell you something that people are getting a little bit of the logic confused. If these numbers were not equal, they obviously are, but if they were not, I've been having a lot of people telling me, oh, well, that means it's not both or neither. I want to clear the air about this right now, guys. Neither is always an option. You can never take neither off the table based on this initial conversation. So you do need to know, right? So if the dimension of V is less than K, then in this case, it cannot be Li. It's too many vectors compared to the size of your vector space. So this could not be Li. Another way of saying it is, in this case, it is a spanning set or neither. Those are the only two possible correct answers. Okay, if the dimension, and this is already, I already made a nice table for you of this, so this is just review. But I'm just putting it down again so we can really make sure you know this. This is a major point. If K is less than the dimension of V, that means I did not give you enough vectors. That means there's no way that these vectors could span the space. So in this case, the correct answer must be either Li or neither. Okay, and then as we just discussed, if the dimension of V is equal to K, then it's both or neither. So what you're noticing here, guys, is that neither is always on the table. The neither option has to always be there. Okay? But in this case, since the dimension of V is equal to K, we are down here in the both or neither scenario. Okay, so now I'm ready for somebody to tell me what I should do to figure out whether it's both or neither. Put it in a matrix, thank you, that's why I was looking at you. Yeah, we're gonna put it into a matrix, and how do we put these into a matrix? Columns, that's the key thing I'm looking for here, guys, is that we arrange them in columns and we grab the coefficients only. Now, I'm gonna start with the first polynomial here, I'm gonna start with the constant term. So it's gonna look like a 1 and a 1 and a 3 and a 3. If you started from the x cubed side, and you did 3 and 3 and 1 and 1, that's not wrong, that's okay. But the main thing is you have to be consistent in all of the polynomials to do it the same way. So whatever order you chose to list the coefficients from the first polynomial, you got to do the same for the next one. So the next one, I have no constant term, 1x squared, and no x cubed term. The next one is a 2 and a -1 and a 0 and a 1. And then the last one, let me move this a little closer for the people online. The last one, we would have -3 and 6 and 6 and 1. And what do I want to augment this matrix with? Yeah, if you're checking both the Li question and the spanning question, you would use zeros and hashtags. Now, we already know that this is both or neither, so if we wanted, we don't have to check them both, right? We only really have to check one of them here. So I wouldn't mind if you only put zeros there, or if you only put hashtags there, because you don't have to do both of these calculations. So what would you suggest I might wanna do next? I can do some EROs. Yeah, okay, so I can do some EROs. The first row is already got a pivot right there in the first entry, so I'll go ahead and leave that as is. So I've got my 1 with a pivot, and I'm going to take the negative of the first row and add it to the second row. Negative of the first row and add it to the second row, so the second row becomes 0, 1, -3, and 9. Yeah. Okay, good. And then 0 and hashtag. All right, great. And then I'm gonna take -3 times the first row and add it to the third row. So it's okay to do multiple EROs in one step. So -3 times the first row added to the third row gives me a 1, 0, a 1, a -6, and a 3. No, 15, right? 15, and then I have 0 and hashtags, okay? And then for the last one, I take -3 times the first row and add it to the fourth row. So I have 0, 0, -5, and 10, I believe. And we have 0 and hashtag, so I'm getting there, but I'm not quite done yet. I need to do one more step of EROs, I guess. The first 2 rows are good to go. I don't want to play around anymore on the first 2 rows. So I'm going to leave those. I'm just going to recopy those exactly the same. But I'm going to take the negative of the second row and add it to the third row. So I'll have a 0 and a 0. Negative of the second row adding to the third row, I get a -3 here and a 6 here. And 0 and hashtag, and then the bottom row 0, 0, -5 and 10 and 0/hashtag. Technically, this -3 and 6 is going to be a pivot on that -3, but what I really want you to notice is that the bottom row, which has -5 and 10, is actually proportional to the third row now, which is -3 and 6. So if I did another ERO, this row would go away. If I, for example, if I did A3, 4 of -5/3, right, I would just 0 out that bottom row. Based on that, what are you gonna tell me? It's neither, because you have a free variable. You have a free variable right here. We could call these, C1, C2, C3, and C4 would be free. C4 would be free, and so the answer here is neither. It's not a spanning set, and it's not Li. So that is gonna prompt me to ask you another question. Oh, by the way, before I do another question, a follow-up question, I wanted to ask you, would there have been another way to do this besides all these EROs? Let's go back to this matrix. I'm very happy we did it this way, but would there have been another way where we could have worked with this original setup and figured out whether the vectors were both or neither? Wronskians don't work so well when the matrix is just filled with numbers. Wronskians are used when we have functions that we're working with. So probably not the Wronskian, but the Wronskian is calculated using the trick that I'm thinking about.
I'm not sure if you, by the trick, I was just thinking maybe if you could take the determinant of vector extension.
The Wronskian is a determinant. And so that was what I was thinking of. Guys, anytime I see a matrix that is a square size, I always want to be thinking about that. It's like, oh, maybe I should be using the determinant to do something. Because you cannot take a determinant if the matrix is not square size, but in this case, it is. This is a 4x4 matrix. If we were going to take the determinant of this, if you were going to take the determinant of this, how do you suppose you, of course, we ultimately know the answer is that it is 0, right? Because we did the EROs already, but pretend you didn't know that and this was the matrix you had. How would you find that 4x4 determinant most likely?
Go faster extension.
Right, I would do cofactor expansion, and on which row or column?
On 2, 3.
Column 2 especially looks good because there's 2 zeros in that column. So you remember how, if you need to review cofactor expansion, I really encourage you to do it. I can't imagine 2 hours of a Math 250B final without having to do a determinant somewhere. So more than likely, you need to know how to do this. So just refresh your memory about it, but you want to pick a row or a column that has more zeros because it means you have less cofactors to calculate. At the end of the day, we know, of course, that we're going to get 0 out of this, okay? Because,
Sorry, keep going. When was it that we put the vectors in column?
well, that's exactly what we just did, isn't it? The first vector, the first polynomial is in the first column, the second is in the second, the third is in the third. We actually almost always put them into columns. Right. Even in chapter 9, when you have, a bunch of vector functions and you're trying to build that so-called fundamental matrix that we just talked about in class on Thursday, you're putting them into the columns. When do we put the vectors into the rows? It's not putting vectors into rows. We'd never do that. The only time we're building our matrix row by row by row is if we're taking equations that we want to solve and making an augmented matrix out of them. That's the situation when you would put the entries into row, sort of on a row by row basis. But generally, once we got to chapter 4 and all points thereafter, we're almost always putting these vectors into the columns of a matrix. That's absolutely true. Okay, yeah, it's a good question. So I have another question though, as a follow-up now to this. Since we've done so much work already over here, what I would like to do, so we've said it's neither. If it's neither, that means it's not Li. So since the vectors are LD, I would like to write a linear dependency down. Okay, so that's actually a little step further. So as a follow-up again, write a linear dependency for the vectors in S. Be a good thing to remind ourselves about as well. So I've got my 4 polynomials. If they are LD, what that means, if they're LD, it means we can make them cancel out in a linear combination. And I want to see that. I want to see what is the equation that would get them to cancel out. Yeah, so does anybody remember how to do this sort of add-on step at the end? Once you know that your vectors are LD, do you remember how you write the linear dependency down? So I just remind you here, the linear dependency is going to just look like this kind of an equation, right? C1 times the first vector plus C2 times the second vector plus C3 times the third vector plus C4 times the fourth vector, and it's supposed to be all canceling out. And the key point though is that the constants are supposed to not be all 0. I can obviously create the trivial equation here by putting all of the C's to be equal to 0. But my point right now is let's not do that. Let's find an interesting linear combination of my 4 vectors. Can we do that by using the work over here? It is like doing a null space because when you're checking for Li, you're making a column of zeros here. So it is a null space. That's an interesting comment, actually, Mo, is that when you're testing vectors for being Li, it's actually not that different than finding a null space of a matrix. There is a connection there. It's not really what I'm talking about right now, but it's a good observation to make that kind of the matrix gets set up the same way. Yeah.
Is it that you would want to solve using back substitution and then those are each of your C's and just put vectors in it?
That's it, exactly. C4 is already a free variable. We can see that the 4th column did not have a pivot. So C4 is equal to T, right? excuse me, and then I can go back to this third row. And I have a -1 and a 2 here, basically. I mean, so the third row is really, just gonna scribble it up here. -3C3 plus 6C4 is equal to 0. That's what this third row is. If I solve that for C3, I get 2 times C4. In other words, 2 times T. So C3 is 2 times T. And now I want to go back to the second equation. So this is the back substitution method, right? The second equation, I'm gonna need another space to make another equation now. From the second row of my row echelon form, C2 minus 3C3 plus 9C4 is equal to 0. And I have to solve that for C2. I have to solve this for C2. Remember, C4 is equal to T. C3 is equal to 2T. So let's see, I believe that C2 would need to be -3T. That look right? Yeah, I think so. Okay, and then finally, I have to figure out C1. That's this row right here. C1 plus 2C3 minus 3C4, that has to equal 0. So I have to solve that for C1. So that would be 3C4, which is 3T, minus 2 times C3. So it's 3T minus 4T, which would be -T, right? You with me? Now, guys, if I asked you for a basis, okay, I'm totally changing topics for a second. I'm not done with that yet. But if I asked you for a basis for the null space of this matrix, going back to Mo's point. If I asked you for a basis for the null space of this matrix, I have basically figured that out right here. This set of constants is the form of the null space. And what I would do to get the basis is what I always do, which is I bust out the variables. So I would bust those out and I would get -1, -3, 2, and 1. And that would be a basis for my null space. By the way, that would mean the null space is one-dimensional. Right? So the nullity, let's just review another thing while we're at it. The nullity of this matrix is 1 because the nullity was the dimension of the null space. Right? Yeah.
With the basis we just found down there. This isn't one of those times where we want to put it in the T3 of R kind of form, we just leave it in that little matrix.
If it's the null space of a matrix, it's not gonna be polynomials, right? You don't talk about null spaces in any context other than you have a matrix and you're talking about a subspace of Rn. In this case, the n, this is a 4x4 matrix, so you're talking about a subspace of R4. So drawing it out with slots like this would be the right way to represent it if it was a null space. Good. Very good point. Yeah, but does everybody remember our good old rank nullity theorem? The number of pivots, which is 3, plus the number of free variables, which is 1, adds up to n, which is 4. So that's just consistent with that. But what I need to do with this, guys, so we're not actually doing that here, because I'm supposed to find a linear dependency. So what you actually need to do now is choose a number for t. And there's only one number that you should for sure stay away from. And that would be 0. You do not want to choose 0 for t because all that will do is make all your constants 0. So what's everybody's favorite number for t? I would choose 1 unless I had a really good reason not to. I'd probably choose 1. So that means that C1 is, using the formulas on the other board over there, C1 is -1, C2 is -3, C3 is 2, and C4 is 1. Let's write that down. So negative of V1 minus 3 times V2 plus 2 times V3 and then plus V4, that should add up to 0. So this would be a linear dependency. I would I would accept it in this form. I guess we didn't really call the vectors v1 through v4. If you wanted to, you could plug them in, right? The negative of, here's the first polynomial. I guess I'll take just a second and write it out. So there's negative of v1, and then minus 3 times the second polynomial, which was x plus x squared, right? And then plus 2 times the third polynomial, which is 2 minus x plus x cubed. And last but not least, plus v4, which is negative 3 plus 6x plus 6x squared plus x cubed. And we now know that that should all cancel out to 0. Unless I screwed it up, that would all cancel out to 0. So you can check it out and make sure that that's really true. Yeah. Okay, so that's a nice little example. Well, this is about where I want to maybe call it. There's so much more to go over. I'll continue again tomorrow. I didn't talk about Newton's law of cooling. By the way, I've decided to completely skip the mixing problems. Just don't even look at that. It's just too much. So, but Newton's law of cooling, that was the very first application we ever saw. So that would be a good one to review. I'll review that tomorrow. I want to review the adjoint method and the Cramer's rule. These are applications of the determinant. So you might need to remember, like, if you want to find the inverse of a matrix. If I want to find the inverse of a matrix, there is a nice way to do it using 1 over the determinant of A times the adjoint of A. And the adjoint of A, if you remember, is the transpose of the matrix of cofactors. And, you know, if you go back to your first, I will say this about myself. I tend to be pretty comprehensive even on my midterms. So if you're like worried that there's gonna be something I forgot to review, looking at those exams, there will be very few holes in the content. Because there will be very few things where I would have been okay with giving you an exam that didn't have you show me something, because I just like everything so much. So if you want to remember how this works, I guarantee you there'll be a problem on the first midterm about it. Do you remember those problems where I gave you, I would do it with this one, except this matrix wasn't invertible. It's a 4x4. Do you remember those problems where I gave a 4x4 matrix and I said, find the 2, 3 entry of A inverse? That kind of question is worth reviewing. So I probably tomorrow going to do one of those. I know maybe not all of you are going to make it tomorrow. I'm going to record this also tomorrow in case you can't make it, or if you just want to get the fast version of this stuff, you could just play my video on 2 times speed or something. But anyway, I know I need to go over that again. The stuff from the third midterm, I'm not talking so much about that because we've just done it recently. You know, if the third midterm didn't go so well, I hope that you are taking that seriously to go back either to do the redo test, or at least to kind of go over the solutions, make sure you understand that. I probably won't do a huge amount with that just because it's pretty fresh, hopefully. That's my plan. But we did pretty good tonight with subspaces, with basis and dimension. Inner product spaces, I thought we did a good review over that. We reviewed the Bernoulli equations, linear equations from chapter 1. That was really helpful, I think. Chapter 2 is just all about EROs. We're always doing those. Can't hardly forget that stuff. So I think that's probably pretty good coverage. So we've made some progress here, but I probably have to go back to my Berkeley days and turn myself a little younger and do an 8-hour review session. Then we really cover everything. But I think this is going to be all I can do for now. I need to go grab something to eat. I'm going to be back in my office though tonight after 7. If anybody does want to chat one-on-one, feel free to do that. Otherwise, I'll see you tomorrow or Tuesday or Thursday, whenever you're taking the final. Thanks, guys. Thank you all for coming.
What time is the class tomorrow?